Okay, let's jump right in. By 2022, the AI revolution was on the verge of hitting a massive, completely invisible wall. Models were getting bigger, context windows were growing, training clusters were expanding left and right. But paradoxically, performance was actually starting to slow down. Welcome to this explainer. Today, we're going to answer one really surprising question. Why did the AI revolution nearly hit a physical wall, and how did one single algorithm break right through it? This is the impossible problem that AI researchers were facing just a few years ago. You had these incredible cutting-edge data center GPUs capable of doing trillions of operations per second. I mean, literally petaflops of mathematical power. But for a huge chunk of their time processing language, those incredibly fast chips were basically just idling. They were sitting there, waiting. But waiting for what, exactly? Well, to really wrap our heads around the scale of this delay, think about this one number, 16 billion. When an AI reads a prompt, every single word, or token, has to check how relevant every other token is, just to understand the context. So if you feed an AI a sequence of 128,000 tokens, which is roughly the size of a novel, that requires 16 billion token-to-token comparisons. And the result of every single one of those comparisons has to be written down in the GPU's memory. It creates a staggering, massive data traffic jam. Which brings us to part one, the culprit, the quadratic memory bottleneck. To figure out why this specific math was completely choking our hardware, we need to peek inside the GPU itself. Think of a GPU as having two completely different workspaces. First, you have the high bandwidth memory, or HBM. Picture this as a massive warehouse. It holds a ton of data, like 80 gigabytes, but getting things in and out is relatively slow, moving at about 2 terabytes per second. Then you have the SRAM. Now this is an ultra-fast, tiny little workbench right on the processing chip. It only holds about 20 megabytes, but it operates nearly 10 times faster than the warehouse. The catch? The GPU does all its actual math on that tiny fast desk, so it constantly has to fetch data from the slow warehouse.
And here is the brutal reality of quadratic scaling. Standard attention tries to write down every single token comparison on a giant scratch pad before moving to the next step. At 1,000 tokens, it's not a big deal, maybe 2 megabytes. But at 128,000 tokens, that scratch pad blows up to 32 gigabytes of intermediate scores per attention head. It completely overflows that tiny fast desk and forces the system to rely entirely on the slow warehouse.
So this is exactly where the traffic jam happens. Standard attention forces this massive gigabyte-sized scratch pad to make 4 agonizingly slow round trips to the warehouse. It writes the matrix, reads it all back to turn those scores into probabilities, which is a process called softmax, writes that output, and then reads it again for the final multiplication. The GPU wasn't struggling with the math at all. It was literally suffocating from moving these massive matrices in and out of slow memory. Enter part 2, the breakthrough, tiling and I/O awareness. What if we never materialize the n-by-n matrix at all? This simple, brilliant question is the paradigm-shifting insight behind FlashAttention. Think about it. If the massive n-by-n attention matrix is just a temporary step, and writing it to the slow warehouse is what's choking the GPU, what if we just didn't do it? What if we process the data so efficiently that the giant matrix never actually has to exist in slow memory at all? So how did they pull this off? With a strategy called tiling. Think of it like assembling a massive jigsaw puzzle. Instead of carrying the entire heavy box from the warehouse to your tiny desk all at once, you just bring a few pieces, a single tile at a time. You do the math for that specific block entirely on the ultra-fast SRAM desk, update your running totals, and then throw the temporary scratch pad away. You only take that long walk back to the warehouse when you have the final, finished output. Now, you might be wondering there's a huge hurdle here, right? Because the softmax function usually requires you to see all the scores in a row before you can calculate the final probabilities. So how on earth do you do that if you only have one small tile on your desk? The secret sauce is something called online softmax. It's this beautiful mathematical trick where the algorithm maintains a running maximum and sum. So when a new tile arrives with a higher value, it just rescales the previous partial results on the fly. Problem solved. The impact this had on hardware was immediate and honestly staggering. Standard attention left GPUs so memory-bound that they were barely utilizing 25% of their theoretical compute capacity. But by slashing those slow memory reads and writes, FlashAttention cranked that utilization all the way up to 75%. The GPU was finally unleashed to do what it was actually built for, crunching numbers at blinding speeds. But guys, here is the absolute wildest part you should take away from this. FlashAttention is not an approximation. It doesn't cut corners or simplify the AI model. It is mathematically exact. Aside from tiny, standard rounding differences, it changes absolutely nothing about the model's output. It's just a vastly smarter execution order that gives you mind-blowing speed and memory savings, basically for free.
Which leads us straight into part 3, a living algorithm, co-evolving with silicon.
Because the story didn't just end with version 1. FlashAttention wasn't just a quick software patch. As new hardware hit the market, the algorithm had to morph into this living, co-evolving piece of engineering. Look at how it unfolded. Version 1 fixed the initial memory bandwidth problem on NVIDIA's Ampere chips. But fixing that exposed a brand new bottleneck, compute parallelism, which version 2 had to solve. Then Hopper hardware came along, requiring version 3 to master asynchronous operations. And most recently, Blackwell hardware forced version 4 to tackle asymmetric compute. Every time a new chip solves an old problem, it exposes an entirely new one.
Take the Hopper H100 GPUs, for example. FlashAttention 3 introduced this beautiful, overlapping dance. It literally splits the GPU's execution threads in two. You have producer threads that fetch data tiles from the warehouse completely asynchronously, totally in the background. Meanwhile, consumer threads crunch the math. It's this incredibly advanced ping-pong schedule where memory loading and computation happen at the exact same time, so the GPU never, ever stalls.
And that brings us to a really unexpected twist with NVIDIA's newest Blackwell chips. Hardware doesn't always scale evenly. On Blackwell, the ultra-fast tensor cores, the engines doing the heavy matrix math, got over 2 times faster. But the specialized units that calculate exponential math for that softmax operation we talked about, they stayed the exact same speed. So suddenly your hyperfast math engines are just sitting around waiting for the slower exponential units to catch up. So how do they fix this bizarre, lopsided bottleneck in FlashAttention 4? With a completely ingenious software workaround. The developers literally bypassed the slow hardware exponential units entirely. Instead, they wrote software to emulate that math and ran it on general-purpose units that were otherwise just sitting idle. By shuffling the workload around and having the shared memory traffic, they pushed Blackwell's speeds to a jaw-dropping 1.6 petaflops.
So what does this constant loop of hardware and software co-design actually mean for all of us? Let's wrap up with part 4, unlocking tomorrow's AI.
We can actually quantify this real-world impact right now. If you look at serving a massive model like Llama 70B at 128K context length, FlashAttention drops the required temporary attention memory from an impossible 32 gigabytes down to a tiny 256 kilobytes per head. Those intermediate trips to slow memory dropped to 0. The speed jumps up by 2 to 4 times. This exact algorithmic efficiency is literally the only reason massive book-length context windows are economically feasible today. But we do need to clarify a super important nuance here. FlashAttention is an absolute miracle for the temporary scratchpad, the intermediate math, but it does not solve the storage problem of the KV cache. The KV cache is the actual memory required to remember past conversation tokens, so the AI doesn't have to reread your whole prompt every single time it generates a new word. That memory still grows linearly, and it still needs to be stored in the GPU's slow warehouse. Because of that, FlashAttention is really just one vital pillar in the modern AI inference stack. To actually deploy today's frontier models out in the real world, you need a triad of engineering techniques working together. You need FlashAttention to fix the compute speed and the intermediate memory. You need quantization to shrink the physical size of the model's weights. And you need techniques like page detention to intelligently manage that ever-growing KV cache memory. Together, they make the AI revolution possible. Which leaves us with a pretty fascinating reality. For years, we thought building better AI was just about throwing more raw compute hardware at the problem. But FlashAttention proved that software logistics, exactly how we move data through the silicon, is just as absolutely crucial. We've conquered the memory bottleneck, the parallelism bottleneck, and the asynchrony bottleneck. So as GPU architectures continue to evolve in wild, totally unpredictable ways, I'll leave you with this. If better algorithms unlock today's AI revolution, what brilliant engineering breakthrough is going to unlock tomorrow's? Thanks so much for joining me on this explainer, and always keep questioning how things work.